The work I'll be presenting today is Representation Surgery, the Theory and Practice of Affine Steering. This work was a collaborative effort between Precog at IIIT Hyderabad, ETH Zurich and Google Research. I'm Shashwat Singh. The link to the paper is in this QR code here. Okay, so to give some motivation about what this work is, I first talk about representations. Language models are trained to predict the next token, and in so doing they train to produce contextual representations or vectors of sentences to predict the next token. Now the central high level question that we care about is, can we treat these vectors as well behaved spaces and well behaved multivariate spaces, and can we exploit these properties for debiasing and to control the generation from these language models? And before we go further, I introduced the concept of guardedness. So what is guardedness? Assume that you have a control attribute z, and now roughly we define guardedness as the fact that you cannot draw a classifier on the representations from the language model to classify this attribute z. For example, guarding gender means that you will be unable to tell the gender of a noun based on the representations from the noun. And what is an affine concept erosion? So it's an affine transformation, that is a transformation of the form wx plus b, where w and b are learnt, such that the representations from x are guarded with respect to attribute z. Now what do we want? So like as I had mentioned earlier, we want either we are trying to debias and we are trying to control generation. At a high level, that means make the vectors from a particular distribution look like those of another distribution. And in the application example, it means that make the vectors that would have led to a toxic generation look like in some way, which I will better define later, the vectors from a non-toxic distribution. And we want to do this with the smallest change possible, and this is going to be very, very important, and this is going to determine what we do next. And the reason we want to do that is we want to preserve all semantics that is unrelated to z. So in the sense that like we want to make the smallest change, and like we want the completion to be coherent, but we want it to adhere to the properties that we want it to adhere to. So in the sense that he asked, let's say, John to off, and if we want to change this, we do not want this to be like toxic anymore, but we still want it to be a coherent generation. So we will change it to immediately. That means we want to change something very small, and we want to preserve as much information about the semantics of the sentence as possible, and we operationalize that using the smallest change here essentially. Now to give you some context and related work, so in the field of interpretability and like controllability of language models, you typically either fine tune, which is out of the scope of what we are dealing with, because fine tuning is not interpretable at all. You talk about steering vectors, which is essentially you try to figure out some vector v that, on addition to the output of the language model, will lead to a vector that has the properties we want. And the general literature has often used v as mu naught minus mu 1, where mu1 is the undesirable class mean and desirable class mean. I will go into this more in the detail, but essentially this has been used to guide the generation of an LM without much essentially without much theoretical motivation as to why this works, but it does work pretty well. What this term means is that the average of all the vectors of the sentences you have for class 0, let's say non-toxic, and this means of the average for all the toxic vectors, and just for every input, if you just do the subtraction and addition, you get a vector that is very close to the original one but is not toxic, for example. And other work, since we are trying to make two distributions look the same, finds application in debiasing, and there is like a lot of work in this, which is lease, in that you take two classes and you guard them. You want them to be indistinguishable from each other. Now this debiasing style of work does not care about where your final representations land up. For example, when I am guarding gender, I am only removing the difference between male and female, let's say, assuming binary gender for simplicity. And when we are trying to detoxify, however, we want the guarantee that everything lands up on the non-toxic side. So there is an asymmetry that we deal with that the debiasing literature does not. So yeah. So with that, after having foreshadowed what we are trying to do, I introduce our contributions. So we phrase an optimization objective based on all the different things I have talked about. So just to deconstruct this optimization objective a little bit, it's a constraint optimization, and so this first part is basically saying that we want to minimize the difference between the original vector and the intervened vectors, right? So I had already stated earlier that we want to make the smallest change possible. So the intervention is the change we are making to the vector, and we want to minimize the effect of that. And we say that, okay, you want to reduce the difference between two distributions. So you have, let's say, this tox, non-tox. You want them to look the same. So one aspect of this is that maybe you want the mean of these two distributions to be the same thing, right? So, and that is the first optimization problem, or the first constraint that we propose. We say, what is the smallest change possible such that the mean of the two classes is the same effectively. That is what we are trying to propose. And the search space for us is essentially piecewise affine. That is, so while affine is just WH plus B, piecewise is that we will make a decision, something you get H, else something you get WH plus B essentially. So we want to find the function that makes the smallest change possible for our classification data set subject to this particular constraint, and the solution to that is just this, and we have a proof of that in the paper. I will skip that for this presentation. So essentially what you end up with is just since W star, like the optimal for the optimization objective, turns out to be I, we get mu C dash minus mu C, which I had already talked about. For things that are undesirable and don't do anything for vectors that are already okay, right? So essentially the first thing we did was say that you can reach this expression that seems to work so well. So in the sense that all of these interventions that we are talking about today work on the assumption that you have a classification data set available. So you have access to sentences and their labels, and you want to use this to do whatever intervention that like you're trying to do. You may be trying to debias, you may be trying to control generation. So the assumption is you have sentence and label available. Now the question is, if the language model has a sense of what this label means, in the sense that the representations from the LM encode toxicity as a different dimension, or like gender as a different dimension, then we are proposing to you a way such that just by using this classification data you can essentially design interventions or obtain interventions closed form, right? And when I say mu c and mu c dash, it's basically saying that okay, you have all of these sentences for class 0, you have all of these sentences, okay, let's say class C, and all of these sentences for class C dash, or let's say you have the vectors from them. Then we're saying that mu c dash is actually, and mu c is just, and that's the notation I'll be using from now. So this can be calculated very easily, this like this thing and this thing can be calculated very easily. Together we give you a formula that you can just apply at each inference step to get exactly what you want, right? Now essentially this matches the so essentially this tells you that matching the first moment gives you this, right? Now we go a step further, which is we extend that problem and we say that what if you wanted to match the first and the second moment. So again, to bring you up again, we are trying to make two distributions resemble each other, A, and we have an asymmetricity. So there's a distribution that we like and there's a distribution we don't like. So we want to make the smallest change to the distribution we don't like such that in some ways, and that like a star, what does in some ways mean? It looks like the desirable distribution. Now in the first case that we have already dealt with, this way was matching the first moment, and that works okay. Now in this second case, this means matching first and second moments, that is match the mean and the covariance, right? And this works even better. So this allows us to again in the same way phrase our optimization problem, which is make the smallest change possible. So this is your minimization objective. So you want to make the smallest change possible, so like original vector, intervened vector, and subject to two constraints this time, A, first moment, B, the second moment. So essentially this is like the second moment of the let's say the original nice class and the second moment of the undesirable class, let's say that, right? And with that this problem is again solved, and like the proof of that is outside the scope of this talk, but essentially it leads us to this solution, right? So essentially the smallest change possible so that you intervene in this piecewise affine way, and you solve that optimization problem by hand, you get this particular solution, and this is guaranteed to be the smallest change in this particular phrasing of change, such that these two properties hold. Note that you might recognize this exact expression. It's related to optimal transport. I won't go into the details of that, but it is the solution to the optimal transport problem for two Gaussian distributions, but that's not relevant. Our proof stands for arbitrary distributions, because the claim we are making is only to match the first and the second moments, right? And if you do like some algebra on this, you will see why this works out roughly. Like you can check, and like it shouldn't be very hard. The sigma here refers to just the covariance matrix. Right. So we solve this problem, we get this intervention out, and now this is the intervention we will be using for our experiments to show that indeed our understanding of how these representations organize or work can be used to do stuff. A, we get a no gradient way to cheaply control the generation from the language model. Note that at no process or no point of this entire exercise we ever calculated a gradient for a data set. So essentially a classification data set was enough supervision for us to understand how to control the representations from the language model. And also debiasing, in the sense that you want to guard a particular attribute based on this classification data set, right? So first, experiment 1 is to show how to show that okay, there is like some value here in terms of debiasing, and for that there is like a popular metric for this sort of thing. It's called TRP gap. Just to summarize what this metric means, it's basically saying that any classifier that you have trained should not, so like okay, let's say that you have a multi-classification problem, which is classify profession based on bios, and the guard vector, the guard variable is gender. So we're saying that the gender should not be used to classify profession ever. In other words, you should not be able to see gender, but you should still be able to classify profession relatively well. Another way to rephrase that is that your classifier should have a very small gap in between the two different categorical classes of gender. So your classifier should have a relative so now with respect to the multi-class classification problem, which is Y, we have the, let's say like you have like doctor, you have engineer, etc., etc. So the classifier's judgment of that should be independent of the gender, which is taken care of by this conditioning. How that turns out is that the expectation over this class minus expectation over this class should just turn out to be 0. So that won't mean that the TRP gap for the class of, let's say, doctor is 0. Your classifier cannot, rather the classifier that you learnt does not care about gender when it's trying to figure out the probability for doctor. And then you do this for all classes in your multi-class problem, and finally you get this TRP RMS metric essentially. And we show here that our solution to this problem is like the best across the board, and like we are able to remove gender without affecting the accuracy on the multi-class classification task. So yeah, and now when it comes to controlling generation, we use something called perspective API to essentially mark the toxicity of a full sentence. So the general evaluation goes like this: we generate 25 sentences per prompt. we get this toxicity evaluation, and we keep the most toxic per prompt essentially, and we apply our intervention at every step of the generation process. And all of the other baselines that we're comparing against either have like a full parameter fine tuning, which is extremely expensive, or they calculate like expensive during training time, or they calculate like a huge amount of gradients during inference time, which is very expensive for inference, leading to slow generation. Our method can just be dropped in and gives you like a very strong control anyway, right? So that's that. Now, so essentially, to summarize the insights of our paper, it means we are basically saying that you can use these like global statistics of representations to control the generation and to debias them. Because a lot of these attributes that you care about are already being encoded properly and in an organized way by the representations of the language model. And that's it for the presentation. If you want to contact any of the primary authors of the paper, use the QR code here. Thank you for your attention.